Hello and welcome to another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 8, Lesson 1 on Introduction to Quadratic Functions. Unit 8 is all about these things called quadratic functions, all right? And they're really cool and they're far more complicated than both linear and exponential functions were, the two main types we've looked at so far. So let's jump right into it and start to understand what a quadratic function is. All right, quadratic functions. We've now studied linear and exponential functions. These functions are relatively simple because they are always increasing or always decreasing, right? A line either always is going up or always coming down, and the same is true for an increasing exponential or a decreasing exponential, right? They're either always going up or always going down. Quadratic functions, though, are a little bit different. Now let's kind of take a look at the general form or how we define a quadratic function. It's any function that can be placed in the form y equals ax squared plus bx plus c, where a cannot be equal to 0, so a, b, and c are constants, they're just numbers. A cannot be equal to 0, but b and c can be. All right, now by the way, if that looks kind of familiar, you know, x squared plus something times x plus a constant from our last unit where we did all this trinomial factoring and binomial multiplication and all of that, well, cool, right? Yeah. Now, by the way, these are all good examples of quadratic functions. Y equals 5x squared minus 7x plus 3, that's, you know, fits this bill. A is 5, b is negative 7, c is 3. Y equals x squared minus 5, that might be strange because there's only two terms here. All that means is b is 0, okay? So like the coefficient of the linear term is 0, so we just don't even write it down. Y equals negative 1/2 x squared plus 8x, that's a quadratic function. A is negative 1/2, b is equal to 8, in this case c is equal to 0. We could put a plus 0 there, no problem. Y equals negative x squared minus 9x plus 1, in that case a is negative 1, b is negative 9, and c is positive 1. Okay, so that's one where all three of those constants are there. All right, so it's very important, you know, when you are introduced to a new type of function, to be able to recognize it when you see it, and to be able to kind of understand it. So let's go down to exercise number 1 and start to play around with some quadratic function work. Read the definition above for quadratic functions and answer the following questions. Letter A, why is it important for the leading coefficient to be non-zero? All right, so let me, without kind of bringing it back down, let me write down what a quadratic function generally looks like. And remember, I said in the definition, the b could be equal to 0. The c could be equal to 0. Both the b and the c could be equal to 0. And we'll see one of those in just a bit. All right, but the a can't be equal to 0. Why is it important for the a, the leading coefficient, to be non-zero? Pause the video now and think about it. And let me put it this way. Consider what would happen if a was 0. Well, if a was 0, right, if we had 0 times x squared, that term wouldn't be there, right? So if a was 0, then we would just have y equals b times x plus c. And that would be a linear function, right? This would just be linear. It would not be a quadratic function anymore. The quadratic function has to have a non-zero x squared term. The x squared term has to be there. The linear term doesn't have to be there, or at least it doesn't have to be written down, right? The constant doesn't have to be there. They could both be equal to 0. But the quadratic, the x squared term has to be there. All right, now let's see if you can recognize a quadratic function when you're given a bunch of different functions. Let's take a look at letter C. Circle the choices below that are quadratic functions. All right, well, pause the video now and circle which one of these 4, and there's more than one, okay? Which ones of these 4 are quadratic functions? Take a moment. It's almost easier to think about which ones aren't. So this one certainly isn't. Y equals x cubed plus 2x squared minus 4. Although it's got 3 terms, the problem is it's not a quadratic function because you can't have an x to the 3rd power. That's actually got its own name. It's called a cubic function. We'll look at those briefly in this course, not too much. And this also cannot be a quadratic function because a quadratic function can't have a square root of x in it. That one's not there either. Now, y equals x squared minus 3, that's a quadratic function. Awesome. And y equals 10 minus x squared, that's also a quadratic function. No problem there either. Okay? Let's take a look at letter C. Given the quadratic function y equals 10 minus 3x squared plus 7x, write it in standard form and state the value of the leading coefficient. All right. So we talked in our last unit about polynomials and what it means for a polynomial to be written in a standard form. Now we have a polynomial function, right? In the last unit, we just had a polynomial expression. Now we have a polynomial function, but writing it in standard form is still the same. Right? The only difference is I'm going to still start with that y equals. Now remember, in standard form, we always want to write the highest powered term first, along with its sign, so that's negative 3x squared. Then we want our linear term, plus 7x, and then we want our constant term, plus 10. So this is our quadratic function written in standard form. Y equals negative 3x squared plus 7x plus 10. Now for quadratics, one thing that will be exceptionally important is the leading coefficient. That's the number that is multiplying the x squared, okay? So the leading coefficient in this case is equal to negative 3, right? It's the number that's multiplying the x squared. That's why it's so important to bring the sign along with it. And boy, the difference between a leading coefficient of negative 3 and positive 3 is huge when it comes to the way the function actually acts. All right, one last little piece. Let's take a look at letter D. If f of x equals 2x squared minus 3x plus 1, then find, without using your calculator, the value of f of negative 2. What point must lie on the function's graph based on this calculation? All right, well, this is simply evaluating a function for a particular input. We've done this quite a bit in this course. Why don't you pause the video now and see if you can figure out not only what the value of f of negative 2 is, but also what point must lie on the graph of this function given the calculation and the result that you get. All right, let's go through it. So, as always, when we do function evaluation, all right, f of negative 2, I'm just going to put negative 2 in. Everywhere there's an x, good idea to put parentheses around it each time you see it. All right, I have to remember my order of operations. Keep in mind, exponents always come first, so negative 2 squared is positive 4. Remember, any number squared will be positive except for 0. Negative 3 times negative 2 is positive 6, and then of course I have that plus 1. Taking this in stages, 2 times 4 is 8, plus 6 plus 1, 8 plus 6 is 14, plus 1 is 15. So f of negative 2 is 15. Now remember, with functions, the input is the x value, and the output is the y value. So this is literally, right, we knew that, x was equal to negative 2, and y is equal to 15. So that tells us that the point negative 2, 15 would have to lie on the graph of that quadratic function. All right, that's it. I mean, and that's just, that's true of any function, right? Like if I put an input in and get an output out, then that x comma y point must lie on the function's graph. Speaking about graphs, let's get into them. All right, the repeating nature of quadratic functions, right? So linear and exponential functions either always were going up or always were coming down, so the outputs, the y values, never repeated themselves. Keep in mind, in a function, the x values will never ever repeat, because if they did, it wouldn't be a function. Quadratic functions are very different than linear and exponentials because they have outputs or y values that repeat. And it's best to look at that with the simplest of all quadratic functions in exercise number 2. Let's take a look. Consider the simplest of all quadratic functions, f of x equals x squared. Letter A. fill out the table below without using your calculator. All right, now remember, saying f of x equals x squared is identical to saying y equals x squared. And all this function tells us to do is take the input and multiply it by itself. So if I take -3 and multiply it by -3, a negative times a negative is a positive, and it's +9, right? If I take -2 and multiply it by itself, -2 times -2 is +4. -1 times -1 is 1, 0 times 0 is 0, 1 times 1 is 1, 2 times 2 is 4, and 3 times 3 is 9. Notice, right, how those y values, you're going to see me drawing that out a lot with tables. Notice how those y values repeat. Now, of course, we can graph this. Take a look at letter B. Graph the function on the grid shown. All right, awesome. So let's do it. Right, we've got all these xy pairs, -3, 9, -2, 4. That's simple enough. So -3, 9 is right here. -2, 4. -1, 1. 0, 0. 1, 1. 2, 4. And 3, 9. Now, this is not a linear function. So the last thing that you want to do right now is take your ruler and connect these points with straight line segments. You do not want to do that. What you want to try to do is draw a very smooth curve through all the points. I imagine you might even do a better job than me. I kind of missed that one a little bit. Nice smooth curve with arrows at the top, indicating that this graph goes up forever in both of those two directions. Now let's look at one last little piece and review something right here. Letter C. What is the range of this quadratic function? The range. It's been a little while since we've seen this term. We've been doing a lot of algebra lately and not a lot of work with functions, so it's kind of confusing, right? Remember, with all functions, we have two sets. We have the sets of inputs, which are the domain, right? So just a little review here. The inputs, the x values, are the domain. On the other hand, the outputs, the y values, well, those are the range. So this is asking for what the range of this quadratic function is. Now notice there are no negative y values, no negative y values down there. All the y values on this graph are either 0 or greater than 0, right? 0 is the absolute lowest y value. So we can now say that the range is, right, y is any real number such that y is greater than or equal to 0. If you like interval notation, which a lot of people like, you could do 0, infinity with a parentheses on the infinity. Remember interval notation, right? The number you start at, the number you stop at, so y starts at 0, it ends at infinity. Infinity is never included, but the 0 is, right? Because we did have an output of 0 right there. All right. Now, what's kind of cool, and we'll talk about this more and more, is that basically all quadratic functions kind of look a little bit like that. Kind of look a little bit like that. All right. Quadratic functions are typically more complicated than our last example, no doubt about that. Yet they all have that same general shape, which is known as a parabola, okay? And that's an important term, right? For a line, for a linear function, its graph is called a line. For a quadratic function, its graph is called a parabola. And I'll use the term quadratic function and parabola often interchangeably. Like I might even say, consider the parabola y equals x squared minus 2x minus 8, or something like that. Anyway, let's take a look at a more complicated quadratic function, and this time we're going to eventually bring out our graphing calculator to help us with that. For now though, let's just take a look at the problem. Consider the quadratic function y equals x squared minus 2x minus 8. Letter A, using your calculator to help generate a table, graph this parabola on the grid given. Show a table of values that you use to create the plot. All right, so with things like linear functions where you can use slope and y-intercept to create the graph, with parabolas it's really helpful to create a table of values. So for right now, I'm going to bail out of this program and I'm going to open up my graphing calculator. I already have an f1 of x kind of just sitting there, right? I want to put in my function, which is x squared minus 2x minus 8. So let me put that in. X squared minus 2x minus 8. Now, of course, one of the great things about my graphing calculator is it won't just produce a table of values, it'll also draw a picture of that parabola. Now, I don't see the whole parabola. There's some that's missing down here, so I'd have to modify my window in order to see it. But remember, I'm just using my calculator now to generate a table of values. To do that on the TI Inspire, I'm going to hit Menu, go down to Option 7, which is a table, and put in a split screen table. Split screen table. All right, now, I'm going to eventually put this table onto my paper, but I'm going to have to make the calculator smaller at that point. So before I do that, while I still have the calculator kind of large, let's sort of like take a look at some of these values. Now remember, I'm trying to fit this in on a piece of graph paper that at least the one that I have goes from negative 10 to 10 and negative 10 to 10. So I'm not going to be able to plot the point negative 4, 16. But I will be able to plot the point negative 3, 7, and the plot negative 2, 0, and the point negative 1, negative 5, and 0, 8. So those are the ones that I want to put in my table. All right? So make sure that you've got this graph kind of into your calculator, that you've generated a table, because I'm going to put this on a smaller view where it's going to be harder for you to see. I apologize for that, but I want to be able to keep this thing in front, and I want to be able to go onto my full screen. And now let me get that table in. You can put your table in either horizontal or vertically. It doesn't really matter. X and Y. So when X is negative 3, Y is 7. When X is negative 2, Y is 0. X is negative 1, Y is negative 5. X is 0, Y is negative 8. Maybe make that negative 5 look a little bit better. Scroll down a little bit. When X is 1, Y is negative 9. X is 2, Y is negative 8. X is 3, Y is negative 5. Running out of space. That should be about enough. X is 4, Y is 0. All right, I'm going to put this down here for right now. Now, before we actually plot all these points and draw our parabola, I want you to notice something again. Negative 8, negative 8. Negative 5, negative 5. 0, 0. Had I gone one more out, had I gone to x equals 5, y certainly would be 7. We're going to talk a lot about the symmetry of quadratic functions in a few lessons from now. But you can see it right away, right in that table, right? Negative 8, negative 8, negative 5, negative 5. The only one that's not repeating is that negative 9, and that's a very important point on the parabola. We'll worry about that in a minute. Right now, let's just plot this thing. So I'm going to go over to negative 3, positive 7. Negative 2, 0, negative 1, negative 5, 0, negative 8, 1, negative 9, 2, negative 8, 3, negative 5, 4, 0. And I'm going to even put in that 5, 7, right? And I'm going to draw this nice, smooth curve. Arrows at the top. Excellent. Not too bad. Not too bad. And again, notice how similar that is to our most simple parabola, y equals x squared, right? It's actually the identical shape. I mean, literally the identical shape. It's just been kind of shifted around on the graph grid. All right, just like before, letter B asks me to state the range of this function. Now that we've reviewed range, I'd like you to pause the video and see if you can give me the range of this function. All right, well, again, whether you like interval notation or whether you like set builder notation, it's up to you. Set builder is a little bit trickier. I want to throw that one down though. Y is any real number. And what's true? Well, such that y is greater than or equal to negative 9, right? So our lowest y value is down here at -9, and they just go up from there, right? The range are the y values, y greater than or equal to -9. A lot of teachers will even just take that. Forget about all this. A lot of teachers will just simply take it if you say y is greater than or equal to -9. Perfectly okay way to do it. Now, again, it's been a while since we've worked with a lot of these function features, but let's take a look at letter C. Over what domain interval is the function increasing? Okay, domain interval, right? Domain interval is x values. Now again, we talked about functions increasing and decreasing, and that can be a little bit tricky when you look at a graph like this and you see these arrows pointing up in both directions, right? But remember, when I think about whether a function is increasing or decreasing, I want to move along the function from left to right. So literally, if I kind of started on this function, all right, and I was moving from left to right, I would be going down here, and then I would start to increase over here, right? So I'm decreasing all through here, and then I'm increasing up through here. So over what domain interval is the function increasing? Well, those are any values when x is greater than 1, right? As soon as we hit x equals 1, we've bottomed out, and then we start to increase. So again, just like before, we could say x is any real number such that x is greater than 1. All right, as long as x is greater than 1, right, then our function is going up. Now, real important, letter D. State the coordinates of the parabola's turning point, also known as its vertex. So, right, lines and exponentials don't have vertices or turning points, but all parabolas, all quadratic functions will have one, and only one turning point, also known as a vertex. And it's about the easiest thing to spot. It's right there. Right? It's right there. Simple as that, right? Right here is our turning point, and that's at the coordinate 1, -9. In fact, the y value of the turning point is the only y value that won't repeat on a quadratic function. It's the only one, right? That is the only place where y is equal to -9. And you can really see it in the table, right? Right in the table. Here is my turning point. If I can spell the word turning. Here is my turning point. Sometimes we'll just abbreviate it as TP for turning point, not that other stuff. All right? So you can really see the turning point just in the table. Now, another very important piece of terminology. I'm throwing a lot of terminology at you in this first lesson that we'll keep using as we move on with quadratic functions, right? So letter E, draw the axis of symmetry of the parabola and write its equation below and on the graph. All right, so every parabola has a vertical line, every quadratic function has a vertical line where it looks the same on one side as it does on the other side. And of course, the great thing about it is that that vertical line must pass through the turning point, right? So this vertical line right here is known as the axis of symmetry, oftentimes abbreviated, not surprisingly, as the A.O.S, the AOS, the axis of symmetry. All right, and again, you should understand it, right? From other work you've done with symmetry, if I sort of flipped this parabola across that vertical line, right, then it would land on itself. Another way to look at it, I hate the fact that I've got all these arrows, is that if you literally go the same distance on either side of that line, right, the two y values that you hit are the same, right? So it doesn't matter where you are. If I go up here, right, the same distance on either side, I get the same y value. Now, because the axis of symmetry is a line, it has an equation. And because it's a vertical line, it has an x equals equation. Specifically, x equals 1. All right, it's been a little bit since we've done equations of vertical and horizontal lines. The axis of symmetry on a quadratic function will always have an x equals number because it's a vertical line. Remember, vertical lines have x equals numbers. Everywhere along that vertical line, x equals 1. Horizontal lines, which don't have anything to do with quadratic functions, horizontal lines, on the other hand, have y equals a number. So x equals 1. Simple enough. Now the last little piece, letter F, what are the x-intercepts of this function? These are also known as the function's zeros. Why does this name make sense? As a suggestion, write out their full x, y pair coordinates. Okay, well first things first. We've talked about x-intercepts and zeros before. Take a look at our graph, more nicely drawn here by a computer than what I could do by hand up there. Go ahead and figure out what the zeros of the function are. All right, well, they are right here and here, right? So x equals -2, I think it is, and x equals 4, right? Those are our x-intercepts, also known as our zeros. And the reason that they're called zeros is if you go up here, right, when x was -2, y was 0. When x was +4, y was 0. So they're known as zeros, right? You know, why does this name make sense? Because they are the x values that make y equal to 0. All right? Parabolas can either have 2 zeros because of the shape of the parabola. They can have 1 0, or they can have none at all, right? You could have a parabola that was sort of sitting up here and never ever hits the x-axis whatsoever, right? Has no real numbers as zeros at all. All right, let's kind of keep working with one more situation. All quadratic functions, as I've mentioned repeatedly, have repeated y values that can be seen in both graphs, as we just looked at, and in tables. All right, we're going to be looking at a lot of quadratic functions in tables, as well as just their graphs on our graphing calculator. Let's take a look at one last problem on a table, exercise number 4. The quadratic function f of x has selected values shown in the table below. Letter A, what are the coordinates of the turning point? All right, well, take a look at this table, and given everything that we've talked about, especially in the last problem, see if you can figure out what the coordinates of the turning point are. Well, it's this simple. Look at this table, right? Notice the 12 and the 12, the 9 and the 9, the 4 and the 4. That has to be the turning point, right? You get these repeated y values, and eventually right in the middle of them, right in the middle of those repeated y values, you get that one y value that doesn't repeat. So the coordinates of the turning point are 2, 13. Now, letter B, what is the range of the quadratic function? Okay, well that's the turning point, right? And take a look. The function is going from 4 to 9 to 12 to 13 to 12 to 9 to 4 to -2. I bet if we had the function's value when x was -2, it would also be -2. So what is the range based on this table? Pause the video now and see if you can write something down. Well, in this situation, what's going on, and hopefully you can almost visualize this, is that we've got a parabola looking like this with that turning point at 2, 13, right? We're increasing up to 213, whoops, and then decreasing afterwards, which means y is any real number such that y is less than or equal to 13. Not greater than or equal to, right? There are no y values in that table that are greater than or equal to 13, and you certainly wouldn't want to look and go, well, the smallest y value is -2, so y is greater than or equal to -2. No way. There's no y value in here that gets bigger than 13. Y is less than or equal to 13. All right, let's summarize. We saw a lot in this lesson, right? First, we just saw a brand new type of function, quadratic functions, right? Functions whose highest powered term is x squared, right? Y equals a quadratic polynomial, one where it has to have an x squared, could also have an x to the first, could also have a constant, doesn't have to, but it could, all right? And all of these graphs then have this shape called a parabola, right? And it's really cool because all parabolas kind of look the same. They either sort of look like a U or an upside down U, I don't know. They all have turning points. They all have a vertical line called the axis of symmetry that you could flip it over. And most importantly, they've got this beautiful symmetry where the y values repeat on both sides of that axis of symmetry. Now we're going to get a lot of work with everything that we've talked about today in the next lesson and the lesson after that. For now, I just want to thank you for joining me for another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.